Hello, we are Team BitFlippers from Vakada Sangvi College of Engineering. Our project focuses on improving wildlife monitoring systems by reducing redundant image data generated by camera traps. Our solution to that is in wildlife conservation system, camera traps continuously capture grayscale images, where each pixel is represented using 8 bits. However, many of these images are visually very similar, which leads to unnecessary storage, usage, and increased transmission cost. To solve this problem, we convert each image into a compact 64-bit signature. This is done by comparing adjacent pixel intensities. If one pixel is brighter than the next, we assign as 1, otherwise as 0. This creates a binary pattern similar to a fingerprint of the image. Since similar images have similar pixel pattern, they produce similar signatures. We then compare two signatures using Hamming distance, which counts how many bits are different. If the difference is below predefined threshold, we classify the image as duplicates. The entire system is implemented in Verilog and designed to run on FGPA for real-time processing. Now, coming to the system architecture, my friend Rugved will explain and further elaborate.
This system performs fast image similarity detection using a hardware efficient approach. The input image is first converted to a 8-bit grayscale and then resized to an 8 by 8 grid, giving 64 pixels. These pixels are processed by hash generators that compute features like pixel comparisons and adjacent differences, producing compact 64-bit hashes. We then calculate the Hamming distance between the hashes using an XOR or a bit counter, which tells us how similar the images are. Finally, this distance is compared with a threshold. If it's below the threshold, then the images are considered as similar. Otherwise, they are different.
Coming to the operational challenges we faced. While developing the systems, we faced several challenges. Processing pixel data in real time on FGPA required careful optimization. We had to design an efficient hashing mechanism using limited hardware resources. Another key challenge was ensuring that similar images generate similar signatures. Choosing an optimal threshold for duplicate detection was also important. Additionally, we had to consider the effects of lighting variations and noise in wildlife images along with the limited on-chip memory. Now coming to the simulation,
Now we will see the simulation in Xilinx Vivado itself. Here we have five variables. We have a predefined threshold. We have two hashes. We have the distance, the Hamming distance, and we have finally the output, whether that indicates whether the image is duplicate or not. So now, till 20 nanoseconds, we have set as hash 2 as 000 and hash 1 is 0 throughout. And after 20 nanoseconds, hash 2 is set as 7FFF. Now, the distance is calculated between hash 1 and hash 2 depending on the time. The threshold is set at 0A. Now, for the first 20 nanoseconds, the distance between the first two hashes is 0. And since it is below the predefined threshold, that is 0A, the duplicate variable is 1 or high or true. That is, the images are similar. After After 20 nanoseconds, the distance between the hashes or between the images increases and goes above the predefined threshold. Hence, the duplicate is set as 0. That is, the images are not duplicate, they are different.
coming to the conclusion, the complete implementation includes Verilog source code, test bench, simulation results, and GitHub repo, along with this documentation demonstration video. This system provides fast and hardware efficient solution for duplicate image detection in wildlife monitoring systems. Thank you.